Greetings and welcome to Physical Science at Hack. In this video, we are going to work through the sample problems for chapter 13 in our textbook on nuclear reactions. So now we're going to be looking at changing the nucleus of the atom instead of just interacting the electrons as we did with the earlier parts of the chemistry section of the course. So let's go ahead and get started with our first problem here, which says to give the number of protons and the number of neutrons in the nucleus of each of these isotopes. Well, let's look at what these mean. So in this case, we see that the first atom is cobalt, and it's cobalt 60. Now when we write it like this is the mass. So that is neutrons plus protons. So the number of neutrons plus the protons has to add to 60. And we can look up in a periodic table the atomic number of cobalt, which is 27. And that means it has 27 protons. And we can take 60 minus 27 to give us 33 and say that it has 27 protons and 33 neutrons. And that would be our answer for the first part of the first question, 27 protons and 33 neutrons. We can do the same thing for the others. Potassium has an atomic number of 19. That means it has 19 protons. Atomic number of 40 means the number of protons and the number of neutrons has to add to 40. So we take 40 and subtract the 19 that we know, and that leaves us with 21, so that potassium 40 would have 21 neutrons. And that would be all we need for this problem. The next one, neon 24, again we look up neon in the periodic table, and that would have 10 protons. And since it's neon 24, we'd take 24 minus those 10 protons, means it would have 14 neutrons. And then our last one, lead 208. Look up lead in your periodic table and find out that lead has 82 protons. And then take 208 minus the 82 to tell you that it has 126 neutrons. So 126 neutrons, and that finishes up problem 1, and those would be your answers there, just as always reminding you to explain how you got your answer. So don't just write them down like this. Give me some at least explanation for one of them, telling me how you got that answer. Now the second one builds on the first, and we want to write the nuclear symbols for each of these. Now the nuclear symbols are a little different than what we've written here. A nuclear symbol uses first of all uses the symbol itself for the element. So cobalt is CO, potassium is K, neon is Ne, and lead is Pb. So that's the start, but that's not the end of the nuclear symbol. When you're writing the nuclear symbol, you also write the atomic number to the lower left. So in this case, that's the number of protons that we determined, and cobalt would be 27, neon would be 10, potassium 19, and lead 82. And then at the top in the upper left, we write the atomic mass. So that's just the numbers that come from here that we used in the previous portion. So cobalt would be 60, potassium would be 40, neon would be 24. Let's try those again. Neon would be 24. potassium was 40, and lead would be 204. So those would be the nuclear symbols for each of these nuclei that we previously looked at. Now, our third question again relates to the same set, and now we want to decide whether they are radioactive or stable and give some kind of reasoning for that. So if we look at these from the previous one, the ones that would be most likely would be stable would be those with even numbers of protons and neutrons. So if you recall, let's go back up to the first question. We had even numbers of protons and neutrons for things like neon and lead. So those would more likely be stable than the others. Although you'd also have to watch that neon 24 has a lot of neutrons for a very low element. So looking at lead, we have 86 protons and 82 protons and 126 neutrons. So let's copy that information over here. So that was 82 protons, 126 neutrons, and that's a pretty high mass element. And that is about 1.5 to 1. That's that 1.5 to 1 ratio. So that would likely be stable. So lead would likely be a stable compound here. So lead would be stable. Let's look at some of the other ones. Neon also has even numbers of protons and neutrons, but would likely not be stable because it has too many neutrons. Remember, when you're in the very first beginnings of the periodic table, the lower mass elements, that usually the number of protons and number of neutrons should be equal. Having 14 here, having 14 neutrons and 10 protons, you're up to almost the ratios that you get for things like lead. So this would likely be unstable. And why? It has too many neutrons. So neon 24 would be unstable. We would expect it to be about equal numbers of protons and neutrons. Now the other two are cobalt and potassium. Now these both have, if you recall, cobalt had 27 protons and 33 neutrons. Potassium had 19 and 21. And as you may recall, ones like these that have odd numbers of both protons and neutrons are probably going to be unstable because of that. So odd numbers of protons and neutrons. So they would likely be unstable. So lead would be the stable one, the most likely stable one here. The other three would most likely be unstable for the reasons given. Now, our fourth problem doesn't use those ones. We get something a little bit different here. We're going to write some nuclear decay reactions, and these are for these various isotopes that as they undergo an alpha emission. Now, if you recall, what does alpha emission mean? Alpha emission here means that you are giving off a helium nucleus. So a helium nucleus here, as you give that off, that will then take away 2 protons and 2 neutrons from the atom, and it will take its atomic number down by 2, and it will take its mass number down by 4. So if we look at the first example here, uranium-235 will decay, coming down to 231 mass units, 90 atomic units. And what is that? Well, that is thorium. So that's going to be thorium plus a helium nucleus. So that would be the decay reaction. The uranium would decay into thorium plus a helium nucleus. For radium, you're going to again go down by 4 and go down by 2. So 222 and 86. And what is 2 less than radium on the periodic table? You find out that that is radon, Rn. Plus, again, always going to be, if it's alpha decay, is always going to be a helium nucleus. Plutonium, we'll take that down to 235 and 92. Take that down to 235 and 92. So we have to look up what does 92 become, and you may recognize that from right up above. That is actually uranium plus a helium nucleus. So again, every time you do alpha decay, it is always a helium nucleus that is coming out. Bismuth would go to 210 mass units, 81 atomic mass. And what is 81? Well, 81 is thulium, Tl. So we put Tl here plus a helium nucleus. Thorium we have here is going to be 226 and 88. And 88 is radon again. I'm sorry, 88 is radium that we looked up just before. So 88, we just had radium up here. So thorium decays into radium plus a helium nucleus. And finally, polonium is going to decay to a mass of 206, 4 less than the 210 it had, an atomic number of 82, which is lead. So we put lead in there, Pb, plus a helium nucleus. So that gives us then those those equations, and that would give us the nuclear reactions that we are looking for. So main thing to remember is that in an alpha decay, it is always a helium nucleus that is being given off. Now our last problem asks about the half-life problem. So the half-life of iodine 131 is 8 days. How much of a 1 ounce sample will remain after 32 days? So as with many of these half-life problems, there are multiple ways to do it, but one of the best things to do is to make a table. So we know, let's write over on the side first of all what we know. The half-life is 8 days. And the sample is 1.0 ounces. And we want to get to 32 days. So if we make ourselves a table here with time and the amount, when we start, that's time 0, and we have 1.0 ounce. After 1 half-life would be 8 days, and we would cut that in half. That would be 0.50 ounces. It would be cut in half. Another half-life would be 16 days, and that would cut this down to 0.25 ounces. We still have to keep going. Another half-life would be 24 days, which would cut down to 0.13 ounce. And finally, 32 days, 8 more. So the number we're looking for at 32 days, we'd cut this down to about 0.65 ounces. Keeping 2 significant figures there the whole way, our answer that we're looking for is actually this number right here, that after 32 days there would be that's 0.065 ounces, not 0.65, 0.065 ounces. So we would have a small fraction of it left. The vast majority of it would be gone after 4 half-lives. We would have the vast majority of the material would then be gone. So all you would have left at this point, your answer, 0.065 ounces. So that concludes our sample problem video for chapter 13 on nuclear reactions, and of course is our last sample problem video for the course. I hope this has helped you and will help you working out those homework problems that you're working on for the last homework assignment. So until next time, have a great day everyone, and I will see you in class.